and unforgiving. It's always been and always will be.
It's going to be hard. There's any chance of death. Going in a little can through deep space. It's a very harsh environment.
We think you can come back, but nothing is certain.
There are all sorts of challenges we will face on deep space missions. Communication delays, radiation protection, isolation of the crew.
So it is not surprising that some would have us stay where we are.
There's never going to be zero risk. When you're breaking the bonds of gravity, that's just part of being.
And it is one of the great inventions of all time. That challenge is one that we're willing to accept. Then it is quest for knowledge cannot be deterred.
Space is not just a destination. It changes you forever. It'll be tough, really tough, but we have the right people for the job.
We have pressed the qualities for success in a system after system.
This country of the United States was not built by those awaiting in residence.
Pushed our people past every failure we can dream of. We have never been more ready to meet another. Once again explore beyond our world.
And you will succeed.
Good afternoon. My name is Robert Bullard, and I'll be the moderator for the Human Exploration Panel. First, I'd like to give our panelists an opportunity to briefly introduce themselves, starting with Sam.
Hello, I'm Samuel Schnur. I graduated from Rice, Bachelor of Engineering in '04, joined Johnson Space Center in '05. My current position is I'm training astronauts and flight controllers as part of the Johnson Space Center, specifically for the computers and communication systems.
I am Franklin Chang Diaz, and I am currently the CEO of Astro Rocket Company. We're developing advanced propulsion systems. Before that, I was an astronaut at NASA for 25 years, flew 7 missions on the space shuttle and a couple other spacecraft. Thank you.
Hello, my name is Mark Craig. I started on work for NASA in 1967 as a co-op in the Apollo program here in Houston, and then went on to work on Apollo-Soyuz, the space shuttle, the space station, the Mars rover sample return, and Lunar Mars exploration program as a program manager here in Houston. From there, went on to become the associate administrator or assistant administrator at NASA for exploration, head of the NASA strategic plan, and from there went on to become acting director and then deputy director at Stennis Space Center and associate director here at Johnson Space Center. I went to Purdue University to get my undergraduate school, went to Rice University on a path to a PhD, and then got all my coursework done and learned a lot, and then the shuttle started flying and stopped, and for various reasons. And went to MIT Sloan School, learned a lot about the business side of the business. One thing I'd point out here that, curiously, I was on the startup team for Space Shuttle in 1969, the startup team for Space Station in 1983, the startup team for New Mars in 1990. That gave me a lot of insight and experiences into what goes on in human spaceflight, I think, I'll claim anyway, and I hope to bring that to bear to the panel today. I was the president of the American Astronautical Society in 2005 and was elected to the International Academy of Astronautics. So I've been involved at the professional level in our organization for a long time. One thing we'd point out, SEDS, Students for the Exploration and Development of Space. Does that ring a bell? first panel started talking about that, I'd like to talk a little bit more about it. But you all are in a very key position right now to deal with that. So congratulations on the name you're using. It's very powerful.
Larry Price, Lockheed Martin, one of the big guys, the big companies. But we are a commercial company too, right? I've been at Lockheed Martin about 100 years, I think. So was really fortunate that I started out. My father was an aeronautical engineer and worked on helicopters before helicopters existed. He worked on a program called the Army XR-1. So it was experimental prototype 1. It didn't work. It was a good try. But I just kind of, it was sort of this just around me all the time when I was growing up, and I didn't really know it. But, you know, a young kid, putting wheels on things, rolling them down hills, digging holes in the ground, building fires and stuff. So I was just really fortunate. So I'm really enthused about students being involved in this. What we do, it's really fun, it's wonderful, it's get to build neat machines, you get engineers that solve problems, get to do it with really interesting people that are like-minded. But I really liked the last panel because a lot of it was business. All of this is only there because of what it'll do to drive the economy. And if you think about it, we talked about the airmail. Other stories, you know, the Mayflower leaving Europe, Transcontinental Railroad. This is not a new model. It's really going to go somewhere. And I just feel really fortunate to be part of it at a point where it's really going to change. NASA, I think, has had a few fits and starts, right? I probably shouldn't say this out loud, but I think we only went to the moon to prove we're better than somebody else. Now it's because we're going to lead the country, lead the world. Mark talked about it. We can put all the steps going forward and make all of this happen, and things will follow. I was dying for you guys in the last panel to say something about GPS. Designed to be a navigation aid. Look what it's used for now. That's what's going to happen. We're going to develop things, and smart people are going to spin off and do other things with it. Silicon Valley exists, I think, because we needed high-speed computation. Look at that's booming. So I feel so lucky to be part of this at a time when it's really going to happen. The Congress, the President now all really get it. They're aligned, and we're going to move forward. Not too fast, because we don't want to spend too much money. It's very precious, but we'll move forward methodically. And presidents have been shown to change their mind when they make a decision. And I think there's a real future in what's going on with space. So it's really encouraging to see so much excitement. And what I always say is, you know, we are just a bunch of nerds building cool machines, but it is really going to change the world.
Thank you. I'm David Alexander. I'm a professor here at Rice. I know many of you, and I'm currently the director of the Rice Space Institute. I can say lots of stuff about our students, but hopefully the folks from the companies here will get to see it for themselves a little bit later. I used to work at Lockheed Martin, different division to Larry, but I was at the Advanced Technology Center in California. And one of the things that I really learned from that, I'm a scientist, astrophysics, I could not care less about big pointy things that have flames coming out of the bottom. At least I used to say that until I moved to Houston. But the key thing I learned working, we were building robotic missions to study the sun, so the human aspect wasn't part of what we did. But the key part was, and many of you have heard me say this, is that the scientists and the engineers working together. And the joke I tell, which is actually a kind of true version of what happens, is the scientists go in and tell the engineers what they want to do. And then once the engineers stop laughing, they tell the scientists what they can do. And it's that combination of the practicality with the exploration side. And when everybody's on the same page, the engineers and the scientists, plus the business people and the government organizations, that's when you can make a huge difference. And I think we see Houston is particularly blessed in that regard with the kind of people we have here. And so one of my jobs is to sort of try and make those connections to NASA centers around the country, but also to international centers around the world. And maybe we'll talk a little bit on that as we go. And I think being in Houston, you can't talk about space without the human aspect. And I think we'll see a lot of that in the discussion to follow. So thank you.
All right. Thank you, panelists. So the first question I'm going to throw to Mark. The question is, what is a question that you wish somebody would ask you?
Thank you so much. And here's the question. What the heck is NASA doing today and why? I've done so many different things at NASA. I've been so fortunate over a very long time, 52 years now. One of the things I've done, curiously, as a side venture, was work with themed attraction business, designing theme parks and space-themed attractions. I've learned from them the power of what they call narrative. It's extremely powerful. And if I look at human spaceflight at NASA, this is my take on our narrative and how it shaped what we've done. I think this shouldn't be a surprise to many of you, but it may put it in language that's more helpful and a concept that's more helpful. We were born in the 60s with a race to the moon. And the goal there was not science, it wasn't technology, it wasn't anything. It was to beat the Soviet Union and win a battle in the Cold War, period. It was very difficult, and we did it. Having done that, the human spaceflight program almost frankly went away. In fact, I was fired. I was the last person hired at Johnson, and the Apollo program was fired at the end of it because I was the youngest person. Well, that was a real eye-opener. NASA didn't go away, thankfully, and I think the leadership, well, you know, we've been to this place called space. What do we do there now? How do we learn to live and work there? How do we learn to use it? And that began to shape programs like the Shuttle, Skylab, other programs. And still exists, I think. Human research, we're still learning about how to live and work in space, and always will. And in the 70s then, as other countries began to have capabilities, and we wanted to express, I'll call it soft power, we wanted to lead with that soft power, the country got into international partnerships. And the first one was Apollo-Soyuz in the early 70s, 73. And it grew into Space Lab, Shuttle Mir, the International Space Station. It's a great success. That's still going on, of course. Now what we have going on is, in the 2000s, it's equivalent really, as the U.S. looked around what was happening in space, and it saw now it's not more countries that have space aspirations and capabilities, more companies. And we want to support U.S. industry as they do that. So starting about 10 years ago, which commercial crew NASA began that. So that's my story of the narrative layers of NASA human spaceflight and what it's done, to give you a sense of perspective of 52 years of working on it. About 10 years ago, because I'm invited to speak a lot of places, schools, civic clubs, churches, business organizations, I began getting that message out, and no one knew it. It was very just out of people, but we thought NASA was dying. What's going on here? And that caused me to put together some material to help explain this approach. That no, NASA is evolving to the next, and it's still evolving, and it's the arc of NASA's story. It's extremely powerful. And what the narrative is, the exploration and development of space. Basically, SIDS. That's the narrative today.
And that development is a key part of that.
It is. It's more than exploration. It's development too. And you've heard the last panel talking about that in some detail. I couldn't agree more. What does that mean? And the next, I got one more chart here that I wanted to explain what I mean by exploration and development of space. NASA explores space, uses human space exploration and leads it with commercial and international partners. That's NASA's job, to explore space. Having done that, though, it then, in an innovative and new way, that supports space's commercial development. And that's what NASA's wrestling with now. And then uses that development to advance exploration. So it's an engine moving out from Earth, in my mind. It's explore and develop.
Absolutely.
And
I just want to pause you real quick.
Sure.
I wanted to highlight, I believe Dr. Chang Diaz is working on some technology for that explicit purpose. Would you like to talk about that?
Yes, I'm happy to do that. There are two ingredients that I think are that need to be looked at. And one is power, and the other one is propulsion. Those are the two key elements that will enable this exploration and the development as well. And the power issue is obviously electricity. You know, electricity generation, power generation in space is changing the shape of the way commercial space is being done, because we're moving from chemical propulsion to electric propulsion. And people keep talking more and more about high power electric propulsion. And electric propulsion in the 60s is essentially at the level of 1 kilowatt maybe. Now we're talking kilowatts to hundreds of kilowatts. And that changes the way the business is carried out. because now you can do more commercial work in the vicinity of Earth with propulsion systems that are far more efficient than the chemical rocket that we have. So this is an important one. And the other one that is very important, that seems to be avoided or maybe discussed in a sort of tangential way, is nuclear power. Nuclear power is an essential ingredient for us to truly move beyond the confines of Earth, of the Earth environment, the Earth-Moon environment. Nuclear, and I'm talking about nuclear electricity, nuclear electric propulsion. And that is an area that we're missing. And people are afraid of it. There's been some sort of timid incursions in the field of nuclear thermal propulsion, because we did it in the 60s, but it is a bit of a dead end, because you don't get that much benefit from the use of nuclear power for thermal propulsion. And so we need to take that bull by the horns and grab it and deal with the problem of high power nuclear electric reactors for space. So those are the two pieces that I think is important to bring up.
Thank you. I'd also like to focus on the fact that we have an astronaut up here, and we also have somebody that works on the things that keep astronauts safe. And I was wondering if Mr. Price could talk about some of the things that NASA is concerned about and companies like Lockheed Martin are concerned about when they design spacecraft for human beings, health-wise.
So the previous panel touched on a lot of things, and Mark mentioned bone loss, muscle loss, exercise, radiation protection. So what's really intriguing about building the Orion spacecraft is to be able to support crew for extended periods of time in deep space. So it's all the protection things that we don't really know that much about already, and being able to have enough propulsion to get where you're going and back again, and everybody knows mass is king. You can't ever have as much weight as you'd like to have to do things. Wrapping humans in lead for radiation is not a solution. So the discussion, David had mentioned about scientists coming up with a question and engineers solving the problems. It's trying to solve those problems on everything to keep a human alive for when we go to Mars years. And it's really intriguing just what the electronics has to do, and we're not doing anything that's really extreme technology. Heat shields have been done before, electronics have been done before, but the quantity of software that's on the vehicle to have it be autonomous and flown by the astronauts or by the ground or automatically is really challenging, and when things would break. And what's going on for the last really decade to advance the hardware, the components, even just plumbing. Propulsion is rocket science, but it's just valves and plumbing, and to make these valves work and move the propellant around in the vehicle. Franklin is really right. What we need is a good propulsion system so it doesn't take so long to get anywhere. We're just basically doing, Chinese fireworks with chemical propulsion. And when we went to Pluto, the spacecraft that went to Pluto was, I think I would say, the smallest spacecraft that they could make to do the science, with the biggest rocket that existed. It left the Earth's atmosphere on its way to Pluto. It took, 3 days to get to the moon. New Horizons passed the lunar orbit in 9 hours, and then it still took it, 9 years to get there. We need propulsion and not keep crew alive as long as it takes to keep them alive. But the Orion spacecraft is really a challenge for an engineer to package all the pieces in to solve all the problems, business problems, but all of the human engineering, health sciences, communication. It's been a wonderful challenge.
And if I can add in there, on top of any additional human health concern we may have, the ISS has been a wonderful test bed for learning more about health in space and how to keep people healthy. But we're in low Earth orbit. We can have communication in just a minute. We can have video with surgeons on the ground. If we need to bring crew back, it's 3.5 hours from undocking the Soyuz to getting back down. As soon as we go out there, they're out there, and propulsion can help a lot with that to reduce that time. but still, if they're 3 months out, they're 3 months out there on their own. So trying to anticipate any problems and more so getting the broad-based skills and broad-based design so that we haven't engineered individual solutions for individual problems, but broad-based solutions for potential problems to make sure that the crew will be as healthy as we can make sure of.
Thank you. So that was kind of forward-looking to technologies that we're thinking about. What are technologies within the past 5 years that you think have revolutionized spaceflight? And I'll leave that open.
First, I'd like to just point out that scientists do not create all the problems and engineers have all the solutions. But they would like, the engineers would like to think that way, but no. No, I think the thing that's kind of revolutionized lately, I mean, apart from it's been the big push towards commercial, and then the partnerships with NASA. Obviously, reusability is, I don't think there's anybody in the room who's seen that double booster landing and not got excited about the space program. I also think that the capability in smaller packages has come up. The CubeSat revolution is part of that. And then I think there's a third piece, and that is the capability in the computer systems, for example. You all know the story about how the Apollo program kind of ran on something that was significantly less powerful than your iPhone. But now, with all of this innovation, we're basically turning the iPhone revolution into a space revolution. We can reprocess spacecraft in 6 months. And so the next generation of spacecraft can go up in a shorter timescale. So that development phase is getting shorter. And as we translate that to the bigger items, that's being translated over from the commercial companies working with NASA and putting all that together. So I think those three things, there may be some others are very specific, but broadly speaking, the reusability, the smallness of the packages and the capability of those small packages kind of encompasses most of, I think, the big changes that have happened the last 5 or 10 years or so.
Just to add on that, just a little tiny bit, right? You mentioned Apollo and it had what? That's 100K RAM of memory or so. The Orion spacecraft has 3 million lines of software code between flight code, ground code, and simulation code. And what that vehicle can do and process and retain the capability with very small components and in the radiation environment is really remarkable.
Another future-looking question. Where do you think humans will be in 2050? On the moon? On Mars? Further? Still on Earth?
I think that poses a question. It shouldn't be about where, it's about what. What will they be doing? I think is the key. Ends and means are really important to differentiate. And that's one thing I'd encourage students to think about the ends. What are the ends of something that determine the means? We love destinations, we love rockets. Those are means. What's the end? It's more important. What's the end that's going to take us here? So I encourage to think about what we'll be doing on the moon and Mars.
So I'm really encouraged where NASA has come and the country has come and all the different types of programs in the last 10 years really remarkably. And so I think we'll be past Mars and other planets and have permanent colonies on places like Mars. And I think what will really happen, what's happened, I'm really interested in the last panel and all of the economic drivers that are going to come. That's what's really going to explode this. I don't use that term in space, but it's going to explode the market. And it will really drive it. And there's so many examples of where the government has planted a little bit of seed money, venture capital kind of thing, and then taken off. I don't know about asteroid mining, but evidently there's some asteroids that are like 90% nickel. And if you can capture the nickel and bring it back down to Earth, and it does not have a fluid value like gold, that you can consume all the nickel that you can provide. So things like that, some bright person will come up with a technique and it'll just take off.
On that note, what role do you think, I probably heard this term thrown around, in situ resource utilization. Do you think that there are any companies specifically that could develop a technology to, say, use resources on the moon or Mars to sustain human life?
I mean, I think the most obvious one for that is water. And that's one of the reasons why the South Pole was a strategic target. the Lunar Planetary Institute people in the audience would like us to visit many different parts of the moon for basically to understand the moon. But from the point of view of ISRU, I think water is the kind of primary, whether you turn that into a nickel mining and so on. Yeah, water is water, but it's also hydrogen and oxygen, both of which are rocket fuel. And so if you can actually provide that, if you can, and this is a great opportunity, I think, and there's many different companies looking at this, particularly if you have NASA as an anchor tenant and you have that in-space propulsion focus. Weight, mass is money in the space industry, and so if you don't have to take it with you, it saves you a lot of money, and you can then buy it in there. So I think that's an important aspect. As you think about human exploration and whether there's a human presence on the surface of the moon or the surface of Mars, there's a different aspect to ISRU, which is not necessarily for commercial sale, but to actually build stuff you need in situ. In other words, you can. There's some experiments with some of the regolith in Hawaii, which simulates very close to what's on Mars, building concrete. And so you can actually build landing pads, run roadways, etc., robotically, presumably. And so just how much and what the innovation is really depends on, I think, your generation really is we should avoid focusing too much on the kind of things that Larry and others are doing, because they're leading the way and they need to solve all these problems. When those problems are solved, you can start using those tools to do new stuff that we haven't actually thought of yet. And ISRU is just sort of the raw materials to help you develop the ideas that presumably there'll be a market for, whether it be a commercial hotel, if it was a Motel 8 on the moon, or whether it happens to be a Lockheed Martin, or dare I say it, Boeing, doing other things in space. And so I think it's just a very open environment, just waiting for those ideas.
Okay, we have about 10 or 15 minutes left, so I want to open it up to the audience for any questions.
I guess this is kind of from the more technology side, but is there, because you said like how iPhones have revolutionized our current capabilities, with the advances of artificial intelligence, could you kind of remove part of the factor of like launchers or transportation across the system? Or is that still too far?
Let me take a shot at that at the beginning of it, right? So it's happening right now everywhere, right? One of the examples I love was when we flew the Orion experimental test flight that you can watch on YouTube, Orion split screen. The one part of the vehicle that was not radiation hardened, was not space qualified, was cameras. And we wanted to have cameras on board because humans relate to what they can see, not all these lines of data coming back. And by the way, the cameras didn't work late in the program, and we were scrambling around to get them to have the image right side up and in the frame. But when the cameras went through the Van Allen radiation belt, they upset. And you can see on the YouTube video these streaks that look like cloud, that look like snow coming across the screen. Well, the Orion capsule is full of what's called fault detection, isolation, and recovery autonomous software. And the ground crew, the amazing NASA people, since I'm not NASA, Apollo 13 kind of mentality, when we went through the radiation belt, the cameras upset, shut down. The fault detection software cycled through its process automatically, turned the cameras back on, and they were back with us. We went through the radiation belt 2 more times. The second time we went through, the ground controllers reset the cameras faster than the software did. But there is so much complexity in going on when you're coming into the atmosphere at 17,000 miles an hour. You can't process all of this quickly. Although the vehicle is, so we've got 3 sets of computers that have self-checking pairs, so if any one of them, it knows if it's good or not. Then the 4th computer is a backup computer, which is dissimilar, so you can't have a common mode failure. So different hardware, different software, different coding. Can't do everything, but it can do all the dynamic, complex modes of flight. And then the next backup is the astronauts can fly the vehicle. Now, the engineers don't think they really can, Franklin, but they do have a hand controller and they can fly it if you get to the final thing. But I think autonomy is really there. We can't do this complexity without it.
Sorry.
I'm not sure you're going there, but if you're, why do we even have human spaceflight? Let's send intelligent devices up. Was that part of your question? Well, I'll tell you the answer to that is then it's not human spaceflight. We need humans there to experience it, to share the experience with other humans back here on Earth, period. And we can do a lot of using capabilities, but it's the day we stop sending humans into space is the day we stop going into space, I think, really, as a species.
Real quick one, I just, Neil deGrasse Tyson, I just love to death everything that he writes. And one of the things I think he said was, he doesn't recall a ticker tape parade for a robot yet.
The only thing I would add to that is, if you think about the architecture that we heard from Mark Aya this morning and some of the things that the other panel talked about, those habitats, the habitat spaces that the astronauts are going to inhabit will not be crewed the whole time. And so they have to be autonomously driven, and that requires smart machines. It requires, whether it's this full-fledged AI making decisions, or whether it's just looking for fault detection. You don't want a micrometeorite to puncture your habitat and not have anyone know about it, and have all the oxygen kind of leak out before the astronauts get there on a 4-month trip to Mars. So this combination of the human spaceflight and how they're supported with autonomy and artificial intelligence, machine learning techniques, I think is going to be crucial. And so it's a way of bringing those things together. Whether it ever handles launches, again, it's a level of precision that you have to worry about. But I think a lot of these things are unavoidable, and I think when they can be used effectively for the mission, I think they will be used.
The question was about powering habitats for long term on Mars? Okay. Anyone?
I guess, I don't want to keep dominating the thing here, but so would anyone else like to say something? Sam, you were looking like you were.
He was standing.
So I think part of that goes a little bit towards what we're talking about, autonomy, like we're going to have to fly up robots for. Solar power, we managed to keep Curiosity going long past the original planned missions, so shout out to Amy there for JPL. So those sorts of technologies have already proven themselves on Mars for being able to last months while the crew's up there. And assuming we've got the right support, we've got the right planning in place, I see no reason why we can't sustainably power a habitat before the crew get there.
Lawrence, you brought up a good point. I was wondering, as an outsider, especially since the shuttle was retired, a lot of NASA's best accomplishments have been through robotics, through a lot of the work that JPL was doing. How big is there really, or is it just political political stories, or is there really schism in NASA between those that advocate exploration with robotics versus what your panel is focusing on, especially as it relates to budgets and policies, or is everyone really all on the same team? And a lot of the other kind of like noise you hear is really politicians debating about how best to put a budget in place.
I can answer that one, having lived through it for 30 years. It was the head moon was from the 90s. There are different points of view about the value of humans and robots. At that time, we really worked hard to come together on one understanding of how they could work together. And we did, I think. JPL is a very valued member of the team. In fact, the project I had was a joint NASA JPL JSC project on Mars rover sample return for that very reason. We each had skills, we each had talents, we each had points of view that made a difference, and we've recognized that. And since then, I think it's been just wonderful. I'd say, you talk about all the great accomplishments of NASA, let's remember the International Space Station too, not just robotic devices. Although there have been tremendous robotic device accomplishments. And isn't it wonderful that this country can develop a suite of capabilities and a suite of contributions to humanity in that nature? It's part of being American, I think. I'm very proud of that.
Yeah, I think it's absolutely together. There are things that you You've got to do precursors with robots, send them ahead of time. All the discussion we had about atmosphere, temperature, radiation on Mars, to be able to do that. What's been going on Mars, I think that kind of the other direction, there's maybe an argument that we know more about Mars than we do about Antarctica because of what we're doing with around the surface of Mars. There are orbiters there, permanent presence of orbiters, communication satellites, the rovers on the surface that have lasted so long, and what we've learned about them. It's really marvelous. And the two together, humans and the robotics operating together, is what's going to propel us into the future. They're absolutely mandatory together.
We just talked about the AI and robotic versus of the missions, but we all know that there will be a very limited human workforce for the first construction of the first human outpost. But so how do you envision like the human robotic collaboration in the constructions of the first human outpost on Mars? Not just as precursors.
So if I understand the question, I mean, just to shorten a little bit, is you're going to need both, and how do you envisage these things working together? There's many different ways that can happen. For example, if you have an intelligent system on a habitat that's empty, I go back to this comment I made earlier about it being crewed for only a short amount of time. You can have it monitoring the environment and have a different kind of environment that is human ready or not human ready. The spacecraft on the way taking the crew to that habitat can be monitoring the health of the crew remotely. And again, you can also think of fault detection as fault detection in humans. Are they stressed? Are they getting sick? Are they cognitively impaired? Astronauts are under an awful lot of stress in a lot of the things they do. The psychological stresses as well as physical stresses. That information can be transferred to the new system once you dock, and then it can be integrated in, so they can actually have all that information coming from 4 months of space travel, and then therefore can monitor the individual astronauts directly, in a sense, so that each human is very different. So you need that kind of level of interaction. You need some of the autonomy that can be overridden. You don't, maybe some of you are too young to remember HAL 9000. I tried, we put in a proposal for this very thing, and they wouldn't let me call it HAL 9000. You want the human to be part of the hierarchy, the autonomous hierarchy, but you want them to be the supervisor. You want them to be called what's in autonomy a supervisory role, and so that has to switch over. But a lot of these tasks can be done routinely without the valuable human time being used up in that way. They're going to go outside, they're going to be roving, they're going to be doing EVAs. That system has to monitor the environment. The spacesuits have to monitor the environment, feed that information back to the humans. So the haptic interfaces, the visual interfaces, the oral interfaces, those are all forms of human systems interaction. The old Apollo version of it was make sure that when you push the button, you push the right button, and your big fat finger in your glove doesn't push the other button by mistake. Right? And so it's just a modern version of that kind of thing. And so you have to have them work together with, I think, the authority ultimately being in the human. But those are things that you have to be careful of because, as Larry pointed out, not just in the radiation belt, but there's radiation environments on Mars that could do what they call single event upsets. And that's the kind of thing that you can't prepare for because you don't know how it's going to interact. You can be as radiation hard as you think you are, and you can minimize those effects. How an AI or how a robot responds to those kind of things can be very different from a human. And so they have to kind of learn from each other in that way. And there's lots more that we can talk about in that particular realm.
If I can just add on into that, it's good mention the robots monitor the humans, but also the humans monitoring the robots as well. Every time a crew lands off the ISS, we have crew questions, and we interview them about how their training was, how their software was, how their interactions, and we actively use that information to keep improving the software that we update. So it's not like we'll just send out the robots and send out the people and we're done. As part of the ground control of the human-robot interaction, I expect constant updates as we learn more out there.
Okay, we have time for one more question. I saw your hand first.
My question is on international cooperation. It's really a two-part question. First part would be for Dr. Chung.
This is a very important point. It was hard. It was very difficult when we got to Russia. You know, it happened to be winter and it was very cold. But I mean, the mindset, the psychological chemistry was very cold. In fact, we sat down along a table with the Russians at one end and us on the other, and two interpreters. And basically, they said, you know, why are you here? You know, we don't want you. And we told them we don't want to be here either. But we were told that we had to do it. And they said, yeah, we were told we had to do it too. And so, I mean, it was a forced marriage in a way, which turned out to be a very good thing, because we look at us today, we wouldn't be anywhere without the help of the Russians. So clearly, international collaboration needs to go beyond just the words. You know, we have to really work at it. And you know, now we have maybe a dozen countries that are participating, but there are 180 or so more that are not in the game. And you know, you look at the people who are flying. I mean, you're missing 90% of the population of the planet, and I think that that's a problem. And you know, it's even difficult to even talk about China. We're not doing anything with China. Why? That's wrong. We're not doing anything with India to speak of in human spaceflight. Why? That's wrong. So, I mean, there's a lot to be done, and it all looks great now, but there's a lot more work to be done. So, you guys, young people, you have a lot in front of you, a lot of barriers to overcome.
Let me add what Franklin said, if I could. I started earlier, I went to Apollo Soyuz. You talk about dislike both ways. It was horrible. I mean, it was, I can't point out how horrible it was. What I learned from that was, though, that the common passion of exploring space did away with all those differences. It really did over time. So go forward 30 years. Tom Stafford, who was the commander of Apollo Soyuz, when he was 71, he and his wife Linda adopted 2 teenage Russian boys because Alexei Leonov asked him to. Now that's a relationship, and it's based on passion for space. So yeah, it's tough. It's really important, and we need to cooperate with everyone in this. The common passion for exploring space will make all those differences fade away. I've experienced it over time. It's amazing, and your generation knows that, I think, better than others. So use it. Everyone needs to cooperate in space.
One of my first jobs, the things I worked on out straightly after being hired, was on the automated transfer vehicle built by the European Space Agency. So we had a European vehicle docking to the Russian side of the space station carrying American cargo. So I was part of trilateral meetings between specifically French engineers, Russian engineers, and myself and another American engineer. And we all had that passion for space. I think probably tensions were not quite as high, Dr. Chang. But we all wanted the best docking mechanisms for our focus, and we all wanted that to be the best. We were coming at best from very different angles. So there was distinct disagreements about how to do that. So we had to, one thing I emphasize part of my job is communication. We had to be able to say, okay, there's a lot of circular argument. Let's define the best. Are we going for most efficient? Are we going for lightest? Are we going for easiest build? And helping burrow down from 3 distinct viewpoints, I think made those procedures and made that better than it ever could if just one of those positions had tried to do it alone. And I completely agree that we are missing out on viewpoints right now, and the greater amount of viewpoints we can get, the better products, the better space exploration will be for all of us.
Yeah, let me reiterate that. I mean, it's wonderful that engineers get to solve problems, and they're the good hard things that scientists come up with to do, and we can't think of on our own, but communication is vital. We are much smarter than multiple people. You all know how to do that. You're all doing things in school in small teams. The business aspects of it that Megan and others brought up is what's going to be the engine that drives all of this. And you guys, it's just a wonderful time to be involved. You're the age of people that are going to be landing on Mars and solving the really tough problems, and all of this stuff will be, a century behind us, and the future will be in front of us. It's really exciting right now.
All right, we are out of time. Could we maybe get like 30 seconds to like 1 minute, just final thoughts?
I'd like to have one, especially for the group says, I worked on Apollo. It was extremely difficult. This is your Apollo. It really is the exploration and development of space. It's harder actually than Apollo, I think, in a lot of ways. Don't ever let anybody tell you it wasn't. In Apollo, we had one great advantage. We were the first ones to do it. Now think about that. So there wasn't a previous generation, now you're a bunch of morons, you can't do it, you don't do it that way. You have this amazing set of capabilities that have preceded you, which you need to use, and you are very thankful for them, I think. But in inventing the next, how to explore and to add the layer of development on top of that, it's huge. It's extremely difficult. Using companies in different ways. And all the things Megan talked about the commercial development, that is really, really hard. It's really hard for NASA. It's really hard for companies. It's so exciting. And frankly, I think it'll have a greater impact on human history than Apollo. Apollo's getting somewhere. It was an amazing accomplishment. But we're talking about settling space. That is a huge accomplishment. That'll change the course of history in ways Apollo never did. And that's your challenge. It's really hard, but it's so, so important. And exploration and development of space is key. So it says it's key.
So I think I really did say it before, business communication, working in teams, but the future is yours. It's really exciting. Don't let anybody tell you you can't do anything. Male, female, age, whatever, just go try. And it will be exciting.
Unless your professor's giving you homework to do. I want to go back. We're focused on this panel on, obviously, human exploration and going to Mars, but there's something that Chris said in the previous panel, which I think is, and actually opens it up to many more of you. They will never build a spacesuit for me. I keep asking them. That's $30 million they don't want to spend. But the thing is that if you are trying to put those humans wherever they happen to be in space, the problems and the challenges you face and the problems you have to solve, there are 7.5 billion people on the planet who can benefit from those sustainability technologies, health technologies, all of these different things. And so your imagination should not be just focused on getting people to space and keeping them alive there. It should be how you can take those and solve problems here on the ground, whether it be climate problems, whether it be water reclamation problems, whether it be all these different things. It's a really broad landscape that pretty much anyone, I would say anyone, can get involved with and in. And you don't have to go to Mars to do it.
All of you are here on a pretty nice Saturday afternoon because you chose to come here because you are passionate about space exploration. You have the opportunities now, as mentioned in the previous panel. We need a constant push to keep going out there. We need that interest to be there, not just for this core group in the room, but you can infect the people around you with the same positive passions for space and to help draw them together with the communication beam. What we learn out there will help us down here, and I think that will be a great movement forward.
I guess my feeling is that going to Mars is fundamentally different from going to the moon, and the same formula that took us to the moon doesn't work with Mars, and we need to think through this problem. The chemistry today is an international chemistry. It's different from the binary chemistry of the 60s, where there were only 2 players and the rest of us were just mere spectators, watching this, 2 titans, duking it out in the sky. It is a different problem, different players. We need to be part of a team. We need to learn. I'm talking about the United States. We need to learn to be team players. And so perhaps we could become the leaders, but to be the leader, you have to earn that rank. You cannot assume that you're going into this and you're just going to be the leader because the Almighty just gave you that designation. You have to earn it, and it's a different environment, different players. You have to be a team player. And that's